Work is something done on an object when a force acts on it over a distance. For a constant force and direction of travel, it is given by the dot product of the force vector and the displacement vector, which you can calculate with FD cosine theta. For example, if you pull a block straight across a table 2 meters with a force of 20 newtons, you have done 40 newton meters of work on it. Work has the units Newton meters, which is also equal to 1 joule. When the force is non-constant, you have to integrate the work using the integral of F dot dl. When you plot the force times cosine theta versus the distance traveled, the area under the curve represents the work done. Energy is a property of an object that allows it to do work. Conversely, doing work on an object can give it energy. Before talking about types of energy, let's talk about conservative and non-conservative forces. Conservative forces are one such that the amount of work they do depends only on the final and initial position of the object. Example is gravity. It will do the same amount of work on an object lifted directly up 2 meters as an object which was first lifted up 4 meters and then lowered 2 meters. Non-conservatives do not follow this rule. Most forces are non-conservative. For example, friction will do less work on an object which was slid on a table in a small circle than an object that was slid in a large circle, even though in both cases they end up at the same location. In general, there are two types of energy, kinetic and potential. Kinetic energy is due to an object's motion. Potential energy has to do with an object's position. Potential energy is the result of a conservative force acting on an object and is equal to the negative work done by that force. For example, when an object is lifted against Earth's gravity, gravity does negative work, but its potential energy increases. The object's potential energy increases. The choice of where potential energy is zero can be anywhere and is usually picked where it's most convenient. For the gravity we experience in everyday life, this means you can pick any height to draw a horizontal line and call that the height where gravitational potential is zero. And then the gravitational potential energy of everything else is defined relative to that line. Potential energy is always the result of interaction between two objects, since a conservative force will always involve two objects. Energy comes in many different forms. Kinetic energy is given by 1/2 mass times velocity squared. The faster moving and the bigger an object is, the more kinetic energy it has. There are many types of potential energy. Here are a few examples. Gravitational potential energy at the surface of a planet, the type we are used to living in, is equal to mgh. H is the distance from the height we pick to be zero gravitational potential energy. Gravitational potential energy between two planets is negative big G times the mass of planet 1 times the mass of planet 2 divided by the square of the distance between them. For springs, potential energy is equal to 1/2 kx squared, where x is the distance from the rest length of the spring. Work and energy are intertwined. The change in total energy of an object is equal to the sum of the work done by non-conservative forces on it. When using this relationship, remember that the right side of the equation involves only non-conservative forces. The conservative forces are already accounted for in the total energy term on the left side. Another relationship you can use is the change in kinetic energy of an object is equal to the sum of the work done on it by both conservative and non-conservative forces. In this equation, conservative forces are accounted for in the work term instead of the energy term. Power is defined as the amount of work done per unit time. For instance, if 100 joules of work were done on an object to lift it in 4 seconds, the power would be 25 joules per second. A formula that comes in handy sometimes is power is equal to the force on an object times the velocity of that object. If you know the power being done by a force, you can find the work that it does by integrating p dt, where p is a power as a function of time. The unit of power is joules per second, equal to 1 watt.
2009 M1. A 3.0 kilogram object is moving along the x-axis in a region where its potential energy as a function of x is given as ux equals 4.0 x squared, where u is in joules and x is in meters. When the object passes the point x equals negative 0.5 meters, its velocity is plus 2.0 meters per second. All forces acting on the object are conservative. The total mechanical energy of the object, which here we will state as E, that is equal to the total potential energy of the object and the kinetic energy of the object. We know that the potential energy of the object is given by 4.0x squared, and that the kinetic energy, which Stan stated earlier, is 1/2 mv squared, where v is the velocity of the object. We can plug in negative 0.50 meters for x, and the velocity is 2.0 meters per second. The mass, which was given, is also 3.0 kilograms. So we can just plug everything in and calculate it with our calculator. And the answer that comes out is 7.0. And since there are two sig figs in the original values, we know that it's 7.0, and also energy is measured in joules, so we put J, 7.0 J. So we want to find the location at which kinetic energy is equal to 0. Now, since energy is conserved throughout this whole thing, we know that the total energy must sum up to 7.0 joules. Since kinetic energy is 0, then all the energy that is being accounted for must be potential energy. Thus, the total mechanical energy, which we know is 7.0 joules, must be equal to the potential energy. So we set 7.0 joules equals to the potential energy, which is 4.0 times x squared, and we solve for x. And once we have solved for x, we find that the x coordinate at which the object has 0 kinetic energy is plus or minus square root of 3 meters. We want to calculate the magnitude of the momentum of the object at x equals 0.6 meters. So momentum, which we know from earlier videos, that is mass times velocity. Momentum p is equal to mass times velocity. So we know the mass is 3.0 kilograms. Now we want to find the velocity of the object at x equals 0.60 meters. Now we know that, once again, the total energy is still 7.0 joules. And we know that the sum of potential and kinetic is equal to the total. So then we can solve for the kinetic energy. K is equal to the total energy minus the potential energy. And once we've solved for the kinetic energy, like we plug in the numbers, 0.60 meters and everything, we find that kinetic energy is equal to 5.56 joules. And we also know that kinetic energy is equal to 1/2 mv squared by our energy formulas. And so from that, we can just set them equal to each other. 1/2 mv squared is equal to 5.56 joules. Plug in 3.0 kilograms, and we find that velocity is equal to 1.92 meters per second. Now we want momentum. Momentum is mass times velocity. Mass, 3.0 kilograms. Velocity, 1.92 meters per second. And we get 5.8 kilogram meters per second. So we want to calculate the magnitude of the acceleration of the object as it passes x equals 0.6 meters. Well, acceleration, as we know, is equal to the sum of the forces over the mass m. Now, we know the mass, once again, is 3.0 kilograms, but we need to find the force that is being applied on the object. Now, the force, we know, is the ddx of energy. And so that is the derivative of the u, the potential energy, in terms of x. So we can take the derivative of 4.0x squared, and we'll get that it is, the negative derivative, sorry, and we'll get that it is negative 8.0x. So the force, the magnitude of the force, in this case, is 8.0x. And so acceleration is equal to 8.0x over m, which is the mass. And so we can plug in our numbers, 8.0 times 0.6 all over 3.0, and we get acceleration is equal to 1.6 meters per second squared. A block of mass m over 2 rests on a frictionless horizontal table as shown above. It is connected to one end of a string that passes over a massless pulley and has another block of mass m over 2 hanging from its other end. Our apparatus is released from rest. A. Derive an expression for the speed vb of the hanging block as a function of the distance d it descends. Now the block and pulley system is replaced by a uniform rope of length L and a mass m, with one end of the rope hanging slightly over the edge of the frictionless table. The rope is released from rest, and at some time later, there is a length of y rope hanging over the edge as shown below. Express your answers to parts B, C, D in terms of y, L, m, and fundamental constants.
So for the first part of this AB problem, we're going to derive an expression for the velocity in terms of distance. So we are going to use conservation of energy for this problem, And we know that the overall change in gravitational potential energy is going to be equal to the change in kinetic energy. So we're going to set mgh equal to 1/2 mv squared. Now we can substitute the values that we already know, such as m/2 for the potential energy side, d for h on the potential energy side, and then for the sum of the masses, so m/2 plus m/2, which is just m, for the kinetic energy side. So once we substitute in these values, we can simplify for velocity, which is going to be the square root of g over g times d. So for the second part of this problem, we know that the force of gravity is mg, and we know that the value of the mass is capital M. And now we need to find the force of gravity only for the part of the rope that's hanging. So we're going to do this by taking a proportion by multiplying the force of gravity by y over L. This would give us only the force of gravity for the hanging part of the rope. For part C of this problem, we're going to have to derive an expression for the work done by gravity on the rope as a function of y. And we assume that y is initially 0, and y is the hanging part of the rope. So what we're going to do is we're going to set up an integral expression for work, which is going to be force times distance, or in this case, distance is going to be dy. And then for the work, we are going to substitute the value that we got in part B, which was mg over L times y. After doing this, we can pull out mg over L from the integral, and we're left with y dy inside. And after evaluating the integral, our overall solution is going to be work is equal to mg over 2L times y squared. For part D of this problem, we're going to derive an expression for the speed of the rope as a function of y, which is the amount of rope hanging off the edge. So to do this, we're going to say that the work done on the hanging part of the rope is equal to the change in kinetic energy. And we know that that's equal to 1/2 mv squared. And lastly, for this AP problem, we're going to have to compare the final velocity of the block attached to a massless string compared to the massed rope. And we're going to have to see which one is greater or if they're both equal. So to do this, we're going to use our derived expression from part A, which was velocity equals the square root of gd, as well as the expression derived in part D, which was velocity equals the square root of g over L times y. Now we can substitute L in for y in part D. And once we bring that value inside of the square root, we can simplify to get the square root of gl. And if we substitute L for D in part A, we get the square root of gl as well. So this shows that the final velocity is going to be the same for both values.